Good afternoon, everyone. Yeah, so I'm a little hesitant to take a session right after lunch, so I'll try to keep it, you know, as simple and as cool as possible. So why I took the topic, I just want to give you a brief on that. With the amount of computing power and the data that is available at scale, and all the engineering systems out there, there is an increasing tendency for data scientists to especially move and gravitate towards a very complex solution when a simple solution could solve the problem, right? So, yeah, and Steve Jobs said that being simple, it in itself is complex, right? So simplicity itself is an art, and it takes your experience and it takes amount of knowledge to keep things simple, right? And hence, this talk is going to be about why should we keep things simple as the first go, and why is it even necessary? And then if we have to keep the things simple, then what should we do? Yeah. So this KISS principle, which is keep it simple, stupid, it came from Kelly Johnson, and Kelly Johnson kind of was working, you know, in the aerospace, and he was an aerospace engineer. And he used to tell his team that whatever parts and things like that you design, it should, you know, it should be simple, that somebody, you know, is able to understand and repair it quickly, right? That's the origination of keep it simple, stupid. And then it became kind of a big design principle where a lot of designers use this principle in their you know, day-to-day job, more on the consumer side. So if you keep your product simple, people will be able to learn it easily. So this is a shift from the era where if you have to learn Excel, you know, 15-20 years back, you used to join some center and learn Excel, right? That's how Microsoft, for example, thought about it. From there is a paradigm shift to Apple, where, you know, you are right on the get-go as soon as the phone, as soon as you get the phone on. So this design principle is what we will see, you know, how we can apply this to the world of data science. This is another one, which is Occam's Principle of parsimony. It more closely aligns with the data science world, where what it says is, hey, there can be for an incident a lot of hypotheses, right? But pick up the one which is more probable and which can, mostly that explains it. I don't know how many of you know, this is the famous story that we would have come across in our early days, is there is this hen which is called as Henny Penny, and she is in a forest, and suddenly there is something that fell on her head or whatever, and the hen starts running. And there are a bunch of animals which come across the hen, and then they ask Henny Penny, why are you running? And then says that the sky is falling and that's why they are running. So some animals again start running, and there is a whole commotion in the forest. And finally there is a rabbit or some intelligent animal that goes out and then goes to possibly the crime spot, and then finds out it's not the sky that fell down. It's possibly just the you know, oak seed that fell down. So that's what Occam's principle of parsimony about, right? When a small incident can be explained by a lot of things. Of course, for this case, there could be the sky falling, there could be something else, you know, there could have been a terror attack and things like that, but finally it was just a, you know, an oak seed that fell down. And this is a classic case, especially you know, you are beginning into the field, or especially if you have suddenly a large amount of data at your disposal along with the computing power. For a simple hypothesis, we do tend to overcomplicate it. So we'll apply this Occam's principle of parsimony to data science, and then we'll see simple data science is fine, but why? So the first thing is complexity, you know, depletes robustness, right? It depletes robustness in two ways. One is the mathematical way where it depletes robustness, and the other one is a more practical way, which we'll talk on how it depletes robustness. So for example, moment you have a complex model, moment you talk about a lot of variables at hand and a lot of features at your disposal, and millions of rows on the area of computing, immediately a curse of dimensionality you know, comes into picture. So what happens when you have too many features at hand, then there are your matrix mathematically becomes very sparse, and it kind of gets difficult to optimize a sparse matrix. So even when it optimizes, we don't know how stable the model will be, right? So it deteriorates the stability of the model, and it kind of ends up overfitting the whole thing, right? So hence it is essential that we kind of work with key features, but they are, as long as it explains the problem, as long as it is good enough, it's a great advantage to get going with it. So that's a mathematical way of why we should keep things simple, right? The other reason why things should be simple is a more pragmatic reasons. So imagine a predictive model which has some 5,000 variables, etc. So these 5,000 variables are of course coming from different client systems, different servers operating and all that. So it's very good in a data scientist notebook where they're able to parse everything and show a model which is doing very good. But then you also run into a problem when you productionize this, because now you're talking about stability of data coming from different sources, as well as originating, some of these data are originating at different time periods and so on. So even if one of the pipeline breaks, its chances are that the prediction may not hold true, right? So that's the practical reason of, again, keeping things simple. And yeah, so this is another one. People especially who are dealing with clients or internal stakeholders, where you kind of take your black box models and you take it to people saying, hey, here is a prediction and this is how it works. There is a lot of pushback whenever it comes to a black box model. It's tough to sell something black box, and hence it keeps you away from taking things to a business impact, as compared to keeping things simple, which people can understand very easily. So another thing that you would note is, AI is a field where, at least I believe that, let us take a classic automation, right? Let's take an automation of, let's say, a railway reservation system, or let's take an automation of, a restaurant management system. So these are things where people were doing something, they were doing with pen and paper, and then some process engineer came up with a solution. First they cleaned the process, and then they got a system to work on it. So this is how software engineering works, and this is how it took over certain jobs and certain functions that traditionally were done either manually or were done using paper and pen. When AI came over, what is AI fundamentally trying to take over, right? AI is fundamentally trying to take over the way people think, right? So you are trying to automate a thinking process. You are letting a machine kind of overrule a marketer's decision, because the machine thinks in a certain way. So that's a big shift, right? So people can get away with normal mundane tasks for the things to be run by the machine. But if you think of high-end AI, where we are saying, okay, a decision system itself can be overruled by a given machine, then for that change to happen, for that delta to happen, when somebody has been doing this, let's say a marketer has been sitting and running a campaign for several years now, and then that job of his intelligence of selecting the right people, his knowledge of identifying the best customers for the product, is being taken away from the machine. Now that's a big shift for somebody who's handling that division, and hence it is important that we recognize the fact that we are dealing with people who we are dealing with people who do not know how the machines work, and they have to now take their responsibility and give it to machine and be accountable for it on top of it, right? So at the end of it, the person who has been running the whole marketing team he is still there, right? And he's saying, instead of me, a bunch of analysts in my team making the decisions, I'm just moving that over to a machine. So he's still accountable for the machine, which is kind of taking the decision, and hence it's a big paradigm shift. Now if this paradigm shift is kind of blocked by the fact that, hey, we have a black box model and we are not able to explain what's going on in it, hence there is now a problem to take things forward. So this is one thing that at least the initial solutions need to break, where the solutions are very simple and acceptable whenever, especially in cases where you are at a point where you're questioning human decision making and the machine is kind of trying to take over that part. So the other thing is why things should be simple. Yeah, as an analyst, it gives you a lot of time to sit and analyze the data, uncover a lot of patterns. This again, I see a lot of people, jump into feature engineering and get to the next, algorithm stage, etc. Whereas they could look at data, they could understand, the business problem at hand, and kind of think and do the traditional way of solving a problem, which is, create your features, think about it, do some exploratory analysis, right? So that part is totally missing, because moment a problem comes, there is an immediate urge to jump into a solution, get into an algorithm, put a deep learning model out there and let the model find features, right? So it immediately, without a necessity to make it complex, you kind of tend to make it complex, whereas you could more think about the data, think about the nuances of the business at hand, think about revenues and impacts, etc., and then start crafting the feature. So if the time could be more used there, you will have a very practical and a feasible solution out. B, it would also reach the goal faster, and hence your impacts could be larger. So this is the classic funnel I go by, to get a high return on effort. And if you look at your model performance over the years, you would believe that the maximum amount of performance is coming at the top, right at the point where you are discussing the business problem with the stakeholders, followed by choosing the right metric. I know I've lost years in discussing what is the right metric, because we started out on assuming, hey, conversion rate is the better way, but then there is attributions are not right, your comparison with the baseline is not established. Somebody is trying to say, this is the right baseline or that is the right baseline. Believe me, that should be at least 40 to 60%, even in a well-defined structure, the first two things put together, right? And if it is especially a new organization which is getting into data science, or if it is a new team which is, or it's a new problem which has never been looked upon from a machine learning perspective, it's extremely important that we spend maximum time in the first two buckets, because that is going to give a more practical perspective and also take you closer to a final solution. Then you get little amount of lift by optimizing on trying to choose the right dependent variable, whether that is available, slice the data, etc. Your feature creation is the next place where you should focus on to get the next impact. Algorithm and hyperparameter tuning kind of comes towards the end. So let's say the last two stages, which is algorithm and hyperparameter tuning could be giving you anywhere between, like, let's say 3 to 10%. The bulk of your lift in your models or the business impact that you are creating lies at the layers at the top. Hence, that is not a delegated layer, right? That's not somebody else's job to do it for you. It's a job as a data scientist that you got to do the first 4 very correctly before starting on the algorithm and hyperparameter tuning. And that's where you get a high return on effort. So this will again, if you spend the time rightly at right stage of the problem, by exploring the problem first, by sitting and spending time with where the problem is coming from, and then tuning your models, etc., you would also have enough time in hand to do the right validations before this goes into a high production systems, right? Be it your out of time validations or be it your out of sample validations, etc. This is where I think we should spend enough time, in understanding the model that is being built out of this process, and hence to before you start socializing this with the various stakeholders. I think this is where the next cutoff time could be spent. And in all this, what we see is, since we are spending a time, at the beginning of the journey with a lot of getting a lot of business perspective, and we are also spending a lot of time understanding what the solution that the machine has come up with, it kind of tends to keep the solution also very simple, right? So So this is, fundamentally you get a lot of time to do a lot of value added stuff that can truly contribute value if you keep your solution simple. And as well, mathematically also it's a very sound way of taking things forward. Now we have seen why. Now it is a few thumb rules from my side, at least from my experience, on the how. How do you keep it simple, right? So first important thing is, it's very important to understand the status quo, right? A lot of times, when we take it, we just assume that, hey, there is nothing existing, and then there is a machine learning model that's going to start solving every problem. But there have been people working on those systems. They have established benchmarks. They have established processes. They know the domain. A sort of a roughly equivalent of an expert system already exists. So hence, the first thing to building anything simple and building anything pragmatic is to start from the ground and to start to understand what is the current status quo. Then the next thing you have to investigate before you start typing anything on your IPython notebook is to understand, does this problem even warrant an ML solution? So consider some use cases, right? So let's say a hair shampoo company, for example, wants to run a marketing campaign, and all it wants to do is to retarget its customers who bought their product earlier. Now, if that's all there is to it, and then they don't care so much about response rate, user experience, etc., then you just target everybody. So that doesn't, classic case of where you never wanted a ML solution. And a lot of people, believe me, it may look very simple on this on the slide here, but a lot of times it happens that people build a solid model, a neural network model, figure out how to rank order a neural network model and everything, and then after rank ordering, the business person comes and says, you know what, we don't want any rank ordering, we want to target everybody. This is seemingly simple, but it's a very common use case that happens all the time. Then sometimes it is just plain frequency distribution that all has to be given, right? For example, if there are only 10 reasons why somebody is calling a call center for, and then you want to figure out the top 3 reasons why somebody is calling whenever the person calls, and let's say top 3 calls occupy 90% of the of your use cases, then you don't need any modeling there, right? So model is on the start accurate at 90%. So the value of the model covering the rest of the 10% is questionable, and hence it has to be very well thought and figured out if there is really a use case for for simple problems, and whether even it warrants a machine learning solution. Yeah, the other classic thing is, typically, supervised works very well above unsupervised. So the simplicity on the problem looks, to convert a seemingly unsupervised problem to possibly a supervised problem. And then once you make it a supervised problem, the accuracies are going to be there. It's very easy to explain, etc., right? So we have to figure out at every given solution if there is an outcome variable that can be defined, right? Or if outcome variable cannot be defined, can it be teased out from the data? Or can somebody look at the data, manually label few examples, and then hence that problem can be converted into a supervised problem. That kind of always yields a very powerful solution. Okay, I'll give you an example. In fact, this is from my experience. So we have been trying to work out a recommendation engine, right? And recommendation engine is a classic unsupervised problem. Things like your collaborative starting right from collaborative filtering, and then the neural network way of doing the same unsupervised approach to matrix factorization and things like that. All that comes into picture. But finally, if you have only that happens if you have a Netflix kind of a problem, right? Where there are millions of movies out there, and then there are millions of variations of these movies to be shown. Yeah, then it warrants an unsupervised problem. But a recommendation problem, let's say even bounded by 500 different product categories that you have, or 1,000 categories you have, there may be enough data out there to go build a supervised model in itself. So hence it's extremely important to kind of, try and see whenever there is a problem, can we kind of try to convert it into a supervised problem and try to make a shift from the unsupervised approach. Remember, unsupervised is important, and there are, for example, Google cannot have a supervised model whenever you do a query search on it, right? Fair. But does every problem warrant an unsupervised thing? That's extremely questionable, right? So that is the framework that you need to think of, whether we have to create outcome variables, labels, manually labeled. It may be initially a lot of effort, but it could give you a very simpler and a simplistic, very simpler solution. Yeah, the other thing is, especially with a large engineering system at hand, and petabytes of data and things like that, people do tend to kind of favor, real-time models over batch models. Now, the question that should be asked is that even necessary? Can a model which is predicting, let's say, on July 1st, some predicted variable, will that stand good even on July 31st? Then if that stands good, then you don't need a real-time model, right? Or you don't need a full-blown machine learning model on a real-time scale, right? So can you start with a small batch model and then kind of add few layers if at all a real-time model is required, more as a checks and balances rather than keeping the entire crunching power on the real-time stuff. So with that, my talk is over, and I think I feel this, I see this as I interview people, as I work with various teams, and also as part of various, advising various startups. I do understand that there is an immediate tendency to go complex. There is an immediate tendency to go, at the fall of a hat to pick up a deep learning model and a deep learning solution. The question is, yeah, all that is great. If the situation so warrants, we should definitely do it. But before that, we should, ask ourselves, is that the right approach? Is that the only approach to do, right? So, thanks.
We have 5 more minutes for question and answers.
Sure.
If you have any questions.
Sure.
Hi, Mathangi. Thank you for such an insightful session. So I'm working on an NLP side, on the text mining side. And I see like this, I see two kind of approaches. One is, I can say it's kind of a pretty simple, where I can doing all my steps, starting from the pre-processing to topic modeling and, the triplets and all these things. And I'm doing all these steps on my own. Wherein the second approach is that I'm using a deep learning model and using a lot of packages which are there, pre-trained models like BERT and all those kind of things.
Yeah.
And using both the approaches, if I just get a better accuracy in using deep learning,
Sure.
Should I really go behind that or use that? Or so what is that I should take my decisions?
So you should take your decisions on, does that, first you should have that scale of data for a deep learning model to really make that difference, right? So A, if you have that scale of data. B, you have to check what is the value you are getting by adding a deep learning model vis-a-vis a standard NLP model. Let's say I'm assuming a standard classifier, or let's say you are using some standard Stanford libraries or something like that. So is there an added advantage that you are getting by deep learning model? And if that kind of substantiates the impact that you can drive, if that impact makes sense, if the impact is meaningful, then yeah, maybe wherever you're getting the maximum impact, you should go for it. But before that, you need to also check whether your data is stable and whether those things, and your compute, right? There is also, finally, you want this to run at a certain frequency, or you want to deploy it somewhere. Now, does the compute also kind of support this approach? Those are the things that you would keep your eyes on when choosing, when there is a simple model available, but you still want to go to a complex. The question I would ask is the impact justifiable?
So yes, looks like, but just again the same thing, that the deep learning model looks like a black box. And
yeah, if you have stakeholders whom you got to explain this,
right.
Then start with something simple.
Okay.
Yeah.
That's a better
Yeah.
start.
Yeah.
Thank you.
Yeah.
Hi. So great presentation. Thanks
you.
for, it's good to see the structure, how you have structured it and how you have highlighted the blocks involved in the flow. So not a question, just maybe an add-on in the
Sure.
theme of simplicity maybe. So in checking the validation of our results, right, we have highlighted validation results and cross-validation. I think oftentimes we overlook an manual error analysis as well. So that is a very simplistic way of validating what is
Yeah, so
working.
I agree. There is finally a sanity check that you
Yeah.
do where you kind of look, especially this is the case with clustering algorithms, right? In spite of all your different kinds of plots and visualization and all, finally what defines it's a good clustering or not is by looking at data and seeing if that cluster makes sense. So at every point, simple sanity over a lot of bar plot, this plot and error plots and a lot of lift charts and Gini index and all that, over above all that is your common sense, which is when you look at the data, does that even look sane and is it even correct, or is there any leakage variable and things like that making a difference? Agreed.
Thank you for the presentation.
Sure.
So,
Thank you.
so this is the problem that most of us face in our industry, where we always try to start with the simpler approaches, but it's the business who always wants us to implement the more complex things.
This is the first time I'm hearing a business is preferring a complex
So
solution.
I work for high tech industry, right?
Okay.
So in that
Yeah.
industry, people are they've already tried out the simpler things at their own end, and they want us to try out more of the complex things to see if we can add any advantage on top of what they've already done.
See, for example, consulting companies or where you have a marketing pitch to make and you want to go and sell your solutions that, hey, we have these, they typically, people say, okay, let's have a complex solution, so that we want to say, hey, if your solution warrants a complex problem solving, then we have people who can do that journey as well, right? So that's a different thing. But I'm talking about things where, hey, you have to solve a problem at hand right now, and then that is going to give a business impact. The fastest and the most frictionless path to go through that is to make things simple.
Cool. If
Yeah.
you have any more questions, you guys can ask her later. She'll be outside for a while.
Yeah.
Great. Thank you so much.
Thanks.